Okay, welcome back, everybody. The plan for today is to finish chapter 6, where it's very short. And then if there are not any questions, I'll continue with 7. And then, you'll be ready to roll for the exam on Tuesday. Similar type of setup as the last exam. You'll be given from noon to 10 p.m. So make sure you give yourself plenty of time. It's timed at 75 minutes. Now on Tuesday, as I stated way before, is I will have lecture. However, if you have questions and you haven't taken the exam, feel free to bring them in, or you're more than welcome also to come to my 1 o'clock, because I gave them the same option. Either you come in with some questions, we can answer them, go over them, and if not, everybody's good to go. We just continue with the chapters. So, okay, totally up to you. So for that day, but I will continue with chapters. You'll notice that the first exam we had to move around because the first 3 chapters were a lot of information thrown at you. But I think now things are kind of leveled out a little bit. We'll be good to go. So it won't be all compressed. All right. Well, any questions? Comments, concerns? No? All right. Well, let me hold on 1 second. Something going on with my share thing here. There we go. All right. I was getting at 1 o'clock. I was getting some noise pickup. So if you're having a hard time hearing me, let me know. Maybe there's something around here I need to shut off. I have nothing on, but you never know. Okay, we ended up in chapter. We're talking about the periodic table and some aspects about the periodic table. Up here, we just started to talk about the specific groups that have their own little name. Like group 1A, they're called the alkaline metals. Everybody except hydrogen. Remember, hydrogen is a gas. It's not a metal. And then the group 2A is alkaline earth metals. And then the halogens are way over in the far right of the periodic table. And group 7A, those are called halogens as a general name for those elements in that group. And then obviously the last column, group 5A being the noble gases. Okay. Now the D block, and those are the guys inside the periodic table here listed in green. They have Roman numerals on the titles up on top. However, they are the B. They're called the group B elements. Those have their own little name in general. All of them collectively are called transition metals. Okay. Now, the ones in the bottom there, the 2 rows, they are also called transition metals, but we add the name inner transition metals. Okay, and I'll come back for that. Come back to that in a second. Now, the behavior of these transition metals is not predictable, meaning that with the A elements being in the same group, they therefore had similar reactivities. Okay. And the other aspect was the nonmetals. If you recall, we talked about nonmetals and metals. The nonmetals, all in the same group, would pick up the same number of electrons, and the metals, specifically group 1 and group 2, will lose the same number of electrons. For example, everybody in the group A, metal-wise, that's everybody here, will lose 1 electron. Therefore, everybody in that same group would end up with a positive charge, ionic charge. Now, hydrogen, it will do the same thing. That's why it's not a metal, but it has 1 valence electron, so it would lose that 1 electron and end up with a positive charge. Okay, so we can predict the charge of everybody in that group 1A, and when they lose an electron. The same thing is true for group 2A. We know that everybody there has 2 valence electrons, okay? 2 valence electrons in the outermost shell. And therefore, all the metals there would have a predictable +2 charge. Other metals that we're going to talk about that have very specific charges, I won't give them to you now, but I'll circle them. The zinc number 30, okay, silver number 47, cadmium number 48, and aluminum, okay, number 13. Those 3 right here also have a very specific charge that they would have depending on, when they lose their electrons. Okay, so what that means, there's 16 elements. There's 118 elements here. These 16 elements that I've highlighted have a very specific charge. I call them the sweet 16. You will always know 100% of the time what kind of charge they have once they become ions, okay? Which helps you because those are constant. That will help you predict what its partner's charge would be. But more on that later on. That implies that everybody else in the green here, they have a variable charge. For example, we have basically 3 forms of copper. We have copper in the element with a 0 charge, net charge, equal number of copper is number 29. Let me change the color here so I won't get it confused. Number 29. So it has copper, the even number of protons and electrons. But copper can also lose 1 electron, ending up with a +1 charge. And it can also lose 2 electrons, ending up with a +2 charge. And so that's what we mean by it being unpredictable. We can't say for sure if it's going to be a +1 or a +2. We need more additional information to determine what happened. We'll teach you how to do that too. Another example would be iron. Okay, iron, Fe, there's 2 types. Obviously, we got the elemental iron with a 0 charge, but iron can lose 2 electrons to give you a +2 charge. Okay, and also iron can be in another form where it loses a total of 3 electrons and end up with a +3 charge. All right, so that gives you the idea of what I'm talking about, it being unpredictable with respect to its reactivity and with respect to the type of charge the ion will have. The other ones in blue, predictable, very specific. The good old sweet 16 are there. Let me clear this up. So those are called the transition metals in green, okay? And the 2 others down the bottom are also transition metals, but we say inner transition metals. Why do we say that? Is because of this. If you note the number of number 58, it's right here. Well, it follows number 57, which is right there. And then we got number 90, and then that follows number 89, obviously. So these guys really belong right here. And that the periodic table I showed you, that expands the periodic table, the long periodic table I showed you before. Okay, so we call those inner transition metals. The 2 rows in the bottom even furthermore have a specific name in themselves. The top row are called the lanthanides, okay? And the bottom row are called the actinides. Okay. Now, the lanthanides also have an additional name that people call them, and those are called the rare earth metals. Very rare. And used quite a bit in a variety of different applications, mostly electronic. And then the actinides basically are all radioactive materials. In fact, to refresh your memory, the atomic weight, which is the number, that decimal number below the symbol, that is the atomic weight, which again is the average of the weighted average of all the isotopes for that particular element. And that's why you get a decimal number, because the mass number for those isotopes are whole numbers, okay? Now, everybody in the bottom basically are radioactive. In fact, elements from 93 beyond are all man-made. They put them in a particle accelerator. We got these particles that just traveled almost at the speed of light and smack each other. And create new elements. So, and there's more coming. They're working on them. Only problem, a lot of them are not have very long a long shelf life. They're made for a short period of time and then they break down. Okay, so you may end up with questions as follows. Okay? So you might ask you, what is the alkali metal in the third period? Okay, so you go back and figure, okay, who are the alkali metals? And second of all, where's the third period? Well, let me change my pen here again. We know that there are 7 periods. 1, 2, 3, 4, 5, 6, and 7, aka energy levels. The alkalides are the first group 1 metals. And so therefore, sodium would have to be the alkali metal in the third period. Sodium is right here, number 11. Okay, alkali, third period. The halogen in the second period. Well, the halogens, if you recall, are right here. And in the second period, that has to be fluorine, right? Can't be anything else, so it's fluorine. And then noble gases. Noble gases are way over here in the far right, in noble because they're inert. And we're looking for noble gas in the fourth period, so it'd be 1, 2, 3, and 4. And there's good old krypton, okay? Krypton, not to be mistaken with kryptonite. Right, so, metals, nonmetals. If you ever forget what's what, your reference point on the periodic table that we give you is that stair step. I'm going to share that with you. You see that stair step on the far right? Right here? Okay. All the elements on the stair step, okay, are metalloids. Anything to the left of the stair step, with the exception of hydrogen, not hydrogen, are metals. And everything to the right, which is all in here, are non-metals, including hydrogen. Okay. Now, you might ask, why do I need to know this? Well, this is crucial because of all the compounds that we utilize or we're aware of, there's only 2 types of compounds. Only 2 types. And let me share with you those 2 types. Okay, type number 1 is a combination of a metal and a non-metal. A classic example would be something you put on your French fries, and that is sodium chloride. Okay, that's a combination of a metal and a non-metal. The metal, okay, is sodium. The non-metal is chlorine. In fact, that type of combination has their own little name, and those are called ionic compounds. Ionic compounds, because they're made up of ions. And more importantly, is that the way they interact with each other are like these 2 magnets that I have right here. Okay, we have the sodium with a full plus charge, and we have a chloride with a full negative charge. Okay, they come together and they attract to each other because they're positive and negative, and they have what's called an electrostatic attraction. there isn't any sharing of electrons. They're attracted to each other because of the charge. And they have very specific properties. One of them is these ionic compounds, when you put them in water, they will break apart into the ions and therefore give you, make a solution, specifically water, conductive. It will conduct electricity because pure water is non-conductive. There are no ions in the water, so it won't conduct electricity. But the moment you put in a little bit of ions in there, like sodium and chloride, table salt, it's a solid outside the water, and they get in the water, they break apart, now they form ions, and now they conduct electricity. Okay, so very distinct type of chemical compound, ionic compounds, which is due to a combination of a metal and a non-metal. The other type, that's number one, that's it. Okay, number two, they're straightforward, right? It's the only other combination you can have, really, is a combination of a metal, non-metal, and a non-metal. Okay. Best example there is, guess what? Good old-fashioned dihydrogen monoxide, aka water. Okay. Hydrogen is a non-metal. Oxygen is a non-metal. Okay. Very distinct difference between the ionic compound. Now, the difference here is this. There is an actual sharing of electrons. I'm going to draw a structure with oxygen in the center. I draw this line with the hydrogen on one side, another line on the other side with hydrogen. Those lines represent two electrons that are being shared between the oxygen and the hydrogen. Okay? Water, when you put water in water, it does not break up, dissociate like the sodium chloride did. Okay, it stays intact. Carbon dioxide is another example of a non-metal metal combination. We got carbon and oxygen here. Okay, two non-metals. Those electrons are shared between the carbon and the hydrogen, oxygen, when they're bonded. Okay, they don't break apart when they go into solution. So, that being said, recognizing the combination of a metal and non-metal tells you whether you're going to be an ionic compound or a covalent compound. I forgot to give you the name. A non-metal and non-metal, we have a special name for it. It's called covalent. It's covalent. Oh, this crazy pen. Or molecular. Okay. And they actually form a bond. They're actually connected to each other, and they're actually sharing these electrons. And there's underneath the covalent compounds is either the type that's either these electrons are shared equally or not equally. And that results in either what we call polar covalent compounds or non-polar. Classic example is oil and water. Italian dressing, you let it sit for a while, it gets separated because you know you have an aqueous solution, an aqueous layer, and an oil layer. Okay, the oil is non-polar. Okay, the water obviously is very polar, very polar. They don't mix. Like dissolves like. And in both cases, they're covalent compounds, but totally different properties. Okay. All right, so it's important that you recognize who's a metal, who's not, who's a non-metal, to determine what type of compound it is, and then use that stair step to help you out, to help you refresh your memory as to who's a metal and who's a non-metal. Okay. All right, we're going to talk about the radius of the outermost electron. In other words, the distance between the nucleus and the outermost electron. Okay. Remember, our model is this. There's 7 energy levels. These electrons occupy different energy levels depending on how many electrons. You got 1 electron like hydrogen, you're going to feel that first energy level. Okay. Then comes helium. You feel that. You continue to feel that first energy level until such time you get more electrons. You start filling all the way to 100, and element number 18. You're filling up all the way to the 7th energy level. Okay, so you're getting a bigger compound. So you already know by figuring this out that down the periodic table, the radius gets bigger. Okay, that makes sense, right? As you increase, the radius increases as you go down the column, as you go down the periodic table, because you're filling your electrons into bigger and bigger energy levels, and therefore the radius gets bigger. Okay. All right. So the other trend is a little bit different. That is going from left to right. Left to right, the radius gets smaller. In this case, they're going from right to left. The radius gets bigger. Okay. It's quite interesting why we think that is happening. We'll explain here in a bit. And this is why. As you go across the periodic table, you increase the number of protons. Remember that? And so let's take an example here of let's pick sodium. Sodium's over here. Now everybody's in the third energy level, third period. So go all the way across periodic table, and let's pick argon. Way on the other side. Okay. All right. Now you saw how going down the periodic table makes sense. The radius gets bigger. Now, why is it as you go from left to right, the radius gets smaller? Well, what's the difference here? Sodium has 11 protons, right? And 11 electrons. Argon has 18 protons and 18 electrons. Okay, so obviously argon has more protons than sodium. So there's more positive charge increased as you go across the periodic table. And another way to look at it is if I use these magnets again. All right, I start off with a set of two magnets, right? I put them together, there's a lot of force there. But then if I get a whole bunch of them together, now I got a lot more electrons and a lot more protons. That nuclear force gets strong. And that results in the electrons being pulled in closer to the nucleus. So as a positive charge increases, the electrons that it has get pulled in closer, and therefore results in the atom getting smaller. Okay. So you may be asked questions about this, and the thing is, you might see the question say, don't repeat the trend, but explain why the trend is such. And left to right, simply because you increase the number of proton charges, so that force proton and electron charge increases, radius, electrons get pulled in, radius gets smaller. Down the periodic table, you're just increasing the number of energy levels for your electrons. So obviously you're just making a bigger, you're having a bigger radius. Okay. One way to look at it is using the snowman, where the head, the circles in the head, the mid body, and the bottom represent a radius. So going from the head down to the bottom, you can see the radius gets bigger. So if you take, that's going down the periodic table, so you take that snowman and lay him on the side, that represents the trend of the radius as you go from left to right. The radius atoms on the far left are bigger than the ones on the right. Which brings me to another point. Think about this for a second, because it makes sense when we talk about different property here in a second. I just said, if you're over here on this side, okay, you have more protons, you have more electrons, and you're holding on to those electrons much, much, much tighter than over here, okay? So that means that if I attempt to remove an electron on the far right atoms, it's going to be tough. Okay? It's not impossible, but it's going to take more energy to remove one electron from those elements in the far right than an electron from the elements in the far left, okay? Because the ones in the far left are not holding on to those electrons as tight. So, keep that in mind when we get to this property here in a little bit. This picture here kind of depicts the radius, and you can see, obviously, it's not, one second. Obviously, it's not 100%. Yeah, there's a little bit of exceptions to the rules, but you can see the general trend from left to right, how the radius gets smaller. You have helium up in the top right corner, probably the smallest element that there is. All right. And going down the periodic table, again, you can see how the radius tends to get bigger. Okay. All right. Question might be asked. I got three elements here, O, S, E, T, E. Which one is larger? Okay. Well, to answer that, what I got to do is find them on the periodic table. And they're listed here. They're in group 6. There are 6A elements. And you can see that they're in the same group. So obviously, that means that Te is the bigger element, right? Te would be in the 5th energy level compared to oxygen, which is in the 2nd energy level. So this is in the 2nd, and this is in the 5th. So Te is obviously much bigger with respect to radius. Now the other question is, the second one is magnesium, silicon, and sulfur. So again, to answer that question, we got to find them, and that's listed down here. Well, they're all of them are in the same period. Okay, specifically number 3rd period, 2nd energy level, 3rd energy level. And so you can see magnesium's in the far left, and then all the way into the far right. So the question is, who's got the bigger radius? Well, that would have to be magnesium, because as you go from left to right, the radius decreases because you increase the number of protons as you go to the right, which results in more proton-electron force interaction, pulling the radius in, making it smaller. Okay. All right, there are videos on the website concerning this topic. By all means, take a look at them. Dr. Kim done a very good job with an alternative explanation concerning the radius and what we talked about. Sometimes it helps to hear it a different way. So by all means, do look at it. All right, so we're going to shift gears a little bit. We got 2 more properties here we're going to talk about before we're done. Property number 1 is called ionization energy. Okay. And then the second property we're going to talk about is EN, electronegativity. People tend to get the two mixed up, but let's explain what ionization energy is. If you look at the term ionization energy, just by the simple definition, it looks like it's the amount of energy it takes to make an element an ion. And that's exactly what's happening. We take, in this example, sodium, which is in the elemental form right there, and we hit it with energy because we want to kick off an electron. All right. And we can measure that amount of energy. And by kicking that electron, guess what? We're making an ion. Okay. All right. So the general trend that we're finding is this: the ionization increases up a group. Or you can say it decreases as you go down the group. All right, well, let's think about this for a moment. Okay, let's take group 1. We take lithium, sodium, and potassium. Okay, And we got RB. And no, let's go to cesium. Okay. So everybody's in group 1A. Now, and if we start with lithium, we got second period 2, 3, 4, 5, and 6. That's the respective period that they're in. So obviously, cesium down at the bottom is a bigger one than lithium. All right. Well, question number 1 with respect to what I just wrote here. What do all of these elements have in common? Okay. What is it about the ones I wrote here? Lithium, sodium, potassium, rubidium, yeah, and cesium. What is it that they have in common? What is the one factor that all these elements have in common?
Do they all have the same valence electrons?
Exactly. You're correct. They all have the same number of valence electrons. Okay. That's why they're in the group. They have different number of electrons total. So lithium has 3 electrons, all right? 3 electrons. Cesium is number 55, and cesium has 55 electrons. We go down the periodic table, right? But regardless of how many they have, every one of them has 1 on the outermost shell. For lithium, that 1 happens to be in the second energy level. Okay, and so we look at this. Let me explain this a little bit because I noticed that the first 1 o'clock had a little bit of a challenge, and we'll see if we can address it. Now, what I'm drawing here is the nucleus, and then these circles, well, semicircles, represent the different periods, the different energy levels. Okay, I got 1, 2, 3, 4, 5, and 6. Well, for lithium, well, I can even put hydrogen up here. Let's put hydrogen. It's got 1. So hydrogen's valence electron is in the first energy level. Right. So I'm just going to say H for hydrogen, its valence electron. For cesium, it is way out there in the 6th energy level. Right? So it's 1 electron. So if you look at the relative reference to the distance, I should say, to the valence electron to the nucleus for cesium, compare it to the distance for hydrogen, obviously, hydrogen's electron is a lot closer to the nucleus. Okay? And when you have when you have a charge separated by space, the force between them, the interaction between them is a function of the distance. The closer the distance, the stronger the interaction. The further away, the less the interaction. Okay? And so for cesium, the cesium, that 1 electron is so far away relative to hydrogen that by all means there's very little interaction. So its electron would be removed quite readily compared to hydrogen, because hydrogen's electron is closer in and interacting with the nucleus much stronger than the one than cesium is. Okay, and progressively the same can be said with RB. RB will be right here, number 5. Okay, its electron, the potassium, and then sodium, and then lithium. So their valence electrons will be respectively in the 2nd, 3rd, 4th, and 5th energy level. So again, if I needed to compare the energy to remove that electron from lithium to sodium, it would take more energy for lithium than it would for sodium, because sodium's lone electron is further away to the nucleus. Okay, so that's what they're trying to tell you here. That's what they're telling you. easier to move electrons from a larger atom because their valence electron, their outermost shell electron, is further away from the nucleus and less interaction between the positive and the negative. Okay, so and that explains why the ionization increases as you go up a group, okay, or decreases as you go down the group, whichever way you want to look at it. Works for you, then do it. Tomato, still tomato, whatever. When you go from left to right, okay, the ionization increases again for a couple of reasons. One, what we talked about earlier, the radius, remember, the radius decrease as you go across a period. Remember the snowman? Okay, and so the radius, because the head of the snowman here has a lot more protons and electrons than, say, down here at the bottom of the snowman, it's going to hold on to those electrons much tighter. So they're not going to release it quite readily. It's going to take some energy. Whereas on the far left, not a problem. They don't have that much protons and electron interaction. So you can remove it with less interaction. That's number one. Number two, remember this, long-term memory. Metals want to lose electrons. I can't overemphasize that. Nonmetals want to gain electrons. And so metals, that we go to the far left, they automatically have a property where they want to give up those electrons. So it won't take a lot of energy to get rid of one. Whereas on the right side, the nonmetals, no, they got more protons on their side. And guess what? They're getting closer to the noble gas, which is that magical 8 that they're trying to get. So they're more likely to gain electrons than to give one up. Okay. All right. So, the innate property of metals wanting to lose, nonmetals wanting to gain is part of it. Also, the fact that nonmetals tend to be smaller in diameter, radius, I should say. Diameter, radius, same thing, similar thing. They're talking about the size. And therefore, those electrons are held on to much closer. Tighter, I should say. So if we look at the data, this is actual data that's been measured with respect to removing an electron from an atom. And this is ionization energy. You're measuring the amount of energy it takes to remove an electron from a neutral atom, an element. And so if you look at the periodic table here, we start off with, let me change the color here. Go black. Here's hydrogen right here. First one. It takes roughly, I don't know, we'll call it 14, maybe 13 and change. We'll call it 13 and a half energy units, specifically electron volts, but that's not important. It's energy units. And we look at helium, okay? These two are in the same period. So we're going from left to right. Helium, oh my goodness, almost 24 units of energy as compared to about 13 for hydrogen. All right, so again, helium is smaller in diameter. The electrons are you got 2 protons, 2 electrons. The positive charge is increased, so it's pulling the electrons closer together, so it's hard to get rid of an electron for helium compared to hydrogen on the same energy level. All right, go around the horn, so to speak. Number 3, lithium, that starts down here. There's lithium. It goes all the way across to neon. As you go across the periodic table, the general trend goes up. Yes, there's always, it jumps up and down. Nothing's 100%. Believe me, in science, nothing's 100%. But you can see some of them decrease, some of them increase. But the trend is they go up. So lithium takes about 5 units of energy. Whereas neon, it goes all the way up to about 22 units of energy. Again, neon has 8 electrons around it. It's not going to give up. those electrons very easily, very readily. It will, but it takes at least 21, 22 units of energy to knock off an electron. Furthermore, it makes sense that as we're going from left to right, far left, we're in the metals. And as we go to the right, we get into the nonmetals. Okay, and the nonmetals want to gain electrons, not lose them. We go all the way around. After neon becomes sodium. Sodium's right here. And the general trend again, going across to argon, it increases. Now, that's the general trend. But you can see that the slope of that line, as you go down the periodic table, tends to kind of flatten down. And again, as you get down in this region over here, the elements get bigger and bigger, right? Just by nature of the beast. And those electrons in the outermost shell, there's really no difference, much difference between the elements on the left and the elements on the right. When you get down into the sixth and the 7th period, they're just so big. Those electrons are just way out there. And they don't interact very readily with the nucleus. But in the early parts, where you can see a general trend. But the slope does tend to decrease. Okay. So ionization energy is the amount of energy required to remove an electron from a neutral atom. Neutral atom. That's the important part. Because we're going to talk about what's called electronegativity, which is not a neutral atom. Right, you might be asked the question, okay, which has a higher or larger IE and why? So let's take a look at these three. We got chlorine, aluminum, and magnesium. All right, of those three that are listed, how many are metals and how many are nonmetals? Who can answer that question? And which ones are metals and which ones are nonmetals? Okay. I got the periodic table there, a part of it. Maybe that will help.
Magnesium is a metal.
Okay.
And then, I'm sorry, I don't know what AL stands for.
Aluminum.
Aluminum is also a metal.
You
and then
got it.
Chlorine is a non-metal.
You got it. Okay. So next time you think of aluminum foil, think of Al. Okay, that's aluminum. Okay, both of them are two metals. Okay, one non-metal. Just by default, that chlorine is a non-metal, and we're comparing two metals. Chlorine is gonna have the higher ionization energy because non-metals want to gain electrons. They're holding on to the electrons that they have very tightly. So it's going to take energy for them to pull off an electron. And if you don't recall that, then look at the periodic table and their relative position. They're in the same period, specifically period number 3. Okay. And just like the trend in the radius, chlorine will be much smaller. Again, it has more protons, more electrons, so that nuclear force is stronger and is going to pull the radius in tighter, making the radius smaller, but at the same time, it's going to hold on to those electrons very tightly. So two factors are to be able to answer this. One, chlorine is a non-metal, and just by default, it's going to be a higher one. It's going to require more energy to get an electron. Okay. Second one. If you look these up, you can see they all belong to group 1A, okay? And they're all metals, but they're on the same group. So what they have in common is that they have the same number of valence electrons, okay? Therefore, and they're in different energy levels. So we got lithium in energy level number 2, and RB is in 5. Okay, so our B's valence electron is way out there relative to lithium. So that means that lithium, being the smaller atom, is holding on to its electrons much tighter because its electron is much closer to the nucleus than the other RB, for example. Okay. All right. There are some videos again, also with ionization energy on the website. So by all means, do take a look at them. Now, here's another property with respect to the electrons are all involved here, but this is more geared toward bonding. Okay. And specifically bonding with, remember I talked about two types of compounds, ionic compounds and molecular/covalent compounds. This is more geared toward bonding of those covalent/molecular compounds, okay? And electronegativity is a measure of the ability of an atom to attract electrons onto the cell. We're going to learn that when we got a bond between two elements, okay, that bond, there's a sharing of electrons between those two elements. We're going to learn that the sharing could be equal sharing. There's an equal pull between electrons. So we have a tug of war between two people or persons that are equal in size and equal in this electronegativity. Therefore, in that tug of war, there's a stalemate. Okay, one is not pulling more than the other. However, if you change it up and you change one of those elements into another element, now you have an unequal pulling. Okay, unequal pulling. So one of the elements tends to pull the electrons toward itself more so than the other. This results in a partial, what we call partial positive and a partial negative. Not a full positive and a full negative like the ionic compounds, but a partial, and enough to call it polar. That is why in the example of the Italian dressing, we got two layers. We have an oil layer that those molecules are basically in their bond, they're sharing equally those electrons, and they have what's called a nonpolar character, okay, because of the nature of the bonds. Whereas the water has an unequal sharing because there's quite a disparity between oxygen and hydrogen with respect to this property here called electronegativity, which results in a very polar compound, okay? And so we have polar, nonpolar. Both of them are covalent compounds, but one of them is equal sharing, and the other one is not equal sharing that bond. Now, what do we do to determine the relative electronegativity? Every element has an absolute value, and we're not going to sit here and tell you to memorize 118 values of electronegativity. That'll be the craziest thing to do, I think. Anyway, but if you use fluorine, fluorine is your benchmark. Fluorine, of all the elements there, is the most electronegative element. Okay, there's no other element has more electronegativity than fluorine. That means that fluorine is bonded to anything other than another fluorine. It's going to pull those electrons onto itself much more than its partner is. Okay, that's what that means. Now, we can use fluorine as our benchmark. We want to compare the electronegativity of different elements. For example, if I look at carbon, which is about right there, and nitrogen, which is about right there. And let's say, for example, there is a bond between carbon and nitrogen. Okay, first of all, there are two dissimilar elements. Therefore, we would have what's called a polar bond because there's unequal sharing of that electron. If this was carbon versus carbon, then there's equal sharing because it's the same element, carbon to carbon. Okay, so we end up making a polar bond. Okay. Over here is unequal sharing. So this becomes, oh, excuse me, not paying attention. The carbon-carbon is a nonpolar, and the unequal sharing makes a polar bond. Hence, polar like water, nonpolar like oil. And how we determine that is we look at the periodic table and we ask the next question, because they're two different. Carbon and nitrogen are different. We're going to automatically have a polar bond. But which direction? Who's pulling those electrons much more? So we go to the periodic table, find the position relative to fluorine, see who's closer to fluorine. In this case, nitrogen is. So nitrogen is a lot more, has a lot more electronegativity than carbon, which means that I'm going to draw an arrow here in the direction of nitrogen, which means that nitrogen is going to pull those electrons more so onto itself than carbon. Okay. And that's how we use the periodic table, and the position is the position relative to chlorine to tell us which direction that pull is going to go. All right. This aspect, the electronegativity, it's important, really important, because when we start building and working with writing or compounds, this electronegativity is going to come again. It's a big factor on how chemistry reacts. It's a big factor on the properties of compounds, why certain things are soluble in water and why certain other compounds are not. Why certain things boil at a certain temperature, while certain compounds boil at a maybe lower temperature. And it's all related to this electronegativity. And guess what? It's related to these crazy electrons. All right, so electronegativity is important. Okay, try to make sure you grasp that. Well, with respect to noble gases, they don't have electronegativity, obviously, because their octet is fulfilled, they're done, they're happy. They don't form bonds, and they don't make bonds. Just between you, me, and Zoom here, down the periodic table, noble gases can make compounds because they're so big and the electrons are so far away. But for Chem 130, noble gases are non-reactive. Okay. All right. Ladies and gentlemen, congratulations. Chapter 6 is done. What do we got? How many more? We got 11 more? 9 more? 9 more, excuse me. I was thinking 16. All right. Any questions? Any questions about this chapter we just got done? No questions? All right. Well, I will continue then with chapter 7. Well, you know what? Let's not. Go ahead and, with the exam coming up on Tuesday, I don't want to give you more information. We'll leave it at that. And go ahead. Why don't we just stop it here unless you have questions about any of the other chapters, 4, 5, and 6. We can go over. If not, again, you can bring those questions to Tuesday. Okay. You can bring those questions Tuesday to my 1 o'clock class if you want, and obviously your class this time, so feel free. Also, I do have a class on Friday, which in their case, they're on chapter 5, that SEC, slide 29. So I will finish up also chapter 5 and 6 for them on Friday, and that's between 1 and 3:40. So feel free to, same link, feel free to jump in. if you need some more. And if you have questions, bring them on Friday too. Okay. All right. Any questions? Guess not. All right. It's been a long day for you guys. We'll cut it off here, and then Tuesday, don't forget the exam. Okay. And I will hang around the email a lot closer on Tuesday than I normally do to answer any questions, because I know that's exam day. All right. And again, yes, I will be here either for questions or we'll jump to chapter 7. No. All right, then. Well, you guys have a safe weekend and take care of yourselves. All right.
Thank you.
Thank you.
Thank you.
Thank you all. I'm going to shut her down and let it format for YouTube. All right. Thank you, guys. We'll see you.